Hello everyone, here is another question from IIT JAM Mathematics year 2018, and this is question number 1. The question is as follows: which one of the following is true? Option A is Zn is cyclic if and only if n is prime. Option B is every proper subgroup of Zn is cyclic. Option C is every proper subgroup of S4 is cyclic. Option D is if every proper subgroup of a group is cyclic, then the group is cyclic. Okay, so how do we solve this question? We first start with option A. We know that Zn is cyclic since Zn is generated by 1 model. So we know that Zn is isomorphic to Z by Nz, and it is generated by 1 plus Nz. So by 1 is basically this element 1 plus Nz. So Zn is always cyclic for each n. So this statement says that if and only if n is prime, this is false, because Z6 is prime. Z6 is cyclic, although 6 is not prime. This shows option A is false. Okay, we now look at option C. Every proper subgroup of S4 is cyclic. Okay, so we know that if in particular we take this subgroup, well, we take identity and the permutation 1 2 3 4 and 1 2 3 4, clearly H is a subgroup of S4 and order of H is 4. This element has order 2. This element also has order 2, and also this element also has order 2. Therefore, H contains no element of order 4. Therefore, H is not cyclic. Because if H was cyclic, then it must have contained an element of order 4, since order of H is 4. Okay, therefore H is not cyclic, and this implies our option C is false, because I have given an example of a proper subgroup of S4 which is not cyclic. H is not cyclic. H is subgroup of S4 and proper. This shows, therefore, option C is false. Okay, we now solve option D. Okay, option D is if every proper subgroup of a group is cyclic, then the group is cyclic. So we now show this option is false. We start with the permutation group is 3. It has order 6. Let H be any subgroup of S3 by Lagrange's theorem. Radiativity of H divides radiativity of the whole group, that is 6. Therefore, radiativity of H is 1, 2 or 3. Since H is proper radius, if H is proper, radiativity of H is 2 or 3. Since both of them are prime and we know every group of prime order is cyclic, therefore H is cyclic. This shows every proper subgroup of H is cyclic, but S3 is non-abelian, hence non-cyclic. So this is basically the contrapositive of the statement that every cyclic group is abelian. So this shows that option D is false. Okay, we now come to, so the only option we are left with is option B, and this is the correct option. It says that every proper subgroup of Zn is cyclic. So we prove more general statement. Our claim is that every proper subgroup, okay, we don't even need proper, we can show that every subgroup of Zn is, every subgroup of a cyclic group is cyclic. Okay, so how do we prove this? We start with some cyclic group. Of order n, let G be generated by A and H be a subgroup of G. If H is the trivial group, then H is clearly generated by the identity element, hence cyclic. If H is not identity element, then we claim that. So what is our claim? Our claim is that there exists T positive in the set of natural numbers such that wherever T is in H. So how do we prove our claim? Okay, so since there exists some element outside this identity element in H, let X not equal to E is in H. Clearly X in also in G. This implies X is of the form a to the power y. If y greater than 0, clearly y not equal to 0, as y is equal to 0 implies x equal to e. Contradiction, because we are starting with x not equal to e. Therefore, y is not equal to 0. If y is equal to 0, our claim is proved. If y is less than 0, then e to the power y belongs to h, since h is subgroup, so its inverse is also in h. This implies e to the power minus y is in h, and in that case minus y is positive, therefore our claim is also proved in this case. So combining these two, our claim is proved. Okay, so we now take m to be the minimum of all such t positive for which e to the power t is in h. So clearly e to the power m is in h. This implies that the cyclic group generated by e to the power m is subset of h. We now prove the other part, that is, we now prove h is also subset of the subgroup generated by e to the power m. So how do we prove this? We start with a generic element of h. Since b is also in G, therefore it looks like b is equal to e to the power a for some k. By division algorithm, k can be written as mq plus r, where either r is equal to 0 or r is positive and less than m. So we will show that this case is not possible, which will imply r equal to 0. So how do we show this is not possible? Okay, because r is equal to k minus mq. This implies e to the power r is equal to e to the power k into e to the power minus m whole to the power q. Okay, let us write this as e to the power m whole to the power minus q. This is in h, e to the power m is in h, so its any power is also in h, and h is subgroup, so their product is also in h. This implies e to the power r is in h. But if we take this condition 0 less than r less than m, this condition, if holds, then r contradicts the minimality of the fact minimality of small m, because small m was minimal such integer for which e to the power m is in h, but in this case we would have got e to the power r is in h, and this would contradict the minimality of small m. Okay, therefore r has to be 0. So this is the only possible case. This implies k is equal to mq Therefore, B is equal to a to the power k is equal to a to the power mq is equal to a to the power m whole to the power q is in the cyclic group generated by M. Therefore, H is subgroup of the cyclic group generated by a to the power m. Combining this two part, we get H is equal to the cyclic group generated by a to the power m. In particular, H is cyclic. Thus, we have proved every subgroup of a cyclic group is cyclic. Since Zn is cyclic, therefore its any subgroup is cyclic. So option B is correct.